that the cell opens and then the channels open and then they close and then they don't want to open again. Okay? So what happened is they identified this as what they called an absolute refractory period and a relative refractory period. And what that means is absolute refractory means I am not opening it again no matter what you do to me. Okay? So you are a sodium channel and you just had a big burst of energy and now you're tired and you're not going to open again. Okay? Now it's a little odd because if you think about refractory, I think about it as not going to open again. But they actually have it listed starting at the beginning of the action potential. Okay? So they're saying it's relative refractory from the moment that it opens. But think about it more like I'm not going to open again. Okay? And then we have what we call a relative refractory period. Relative means maybe if you push me hard enough, I will open. Okay? Maybe if you give me enough money, I'll open. Maybe if you make things interesting enough, I will open. So that means that you might be able to open the sodium channels again while you're in the hyperpolarization stage, but not unless you had a massive stimulus. Okay? Not unless you had a massive stimulus. And remember, that means that a ligand is hitting a receptor and letting the sodium into the cell by the stimulus channels. Okay? The stimulus channels. And then if there's enough stimulation, you will be able to get another action potential. So on your picture of your action potential, you need to mark the absolute and relative refractory periods. As far as I am concerned, the absolute period does not end until, like on that one, you get down here. So your line should be somewhere over here. For the end, this is your absolute on this side. Whoops. Sorry, I have bad handwriting. Okay, on the other side of it, you have your relative. Okay? Maybe I will open if it's interesting enough. Okay? Absolute refractory and relative refractory only occurs to sodium channels. Okay? Only sodium channels. Okay. So there's a little definition for you that explains about the relative refractory periods, and we have another little movie.
When the cell membrane is at its resting membrane potential, the activation gates of the voltage-gated sodium ion channels are closed and the inactivation gates are open. Voltage-gated potassium ion channels are closed. Depolarization is initiated by a stimulus which makes the membrane potential more positive, causing the voltage-gated sodium ion channels to start to open. As threshold is reached, many sodium channels open. Sodium ions diffuse across the membrane, causing depolarization. Voltage-gated potassium ion channels also begin to open, but more slowly. Therefore, depolarization occurs because more sodium ions diffuse into the cell than potassium ions diffuse out of it. As the membrane potential approaches maximum depolarization, the inactivation gates of the voltage-gated sodium ion channels begin to close, and the diffusion of sodium ions decreases. The potassium ion channels remain open, and potassium ions continue to diffuse out of the cell. The increased potassium ion permeability lasts slightly longer than the time required to bring the membrane potential back to its resting level. The extra efflux of potassium ions causes the membrane potential to become slightly more negative than the resting value. After the voltage-gated potassium ion channels close, the active transport of sodium and potassium ions reestablishes the resting membrane potential.
Okay, that was a quickie. Sometimes it is easier to have a picture. Sometimes it's easier to have a picture in your head, and now you can think about those sodium channels having a activation gate and an inactivation gate, so that you can see how they close and they don't want to reopen. Okay? Oops. Okay. So I don't like this picture, and the reason I don't like this picture is look where the absolute refractory period ends. It ends just as they close. So do not look at this picture in terms of that, okay? Because that's not correct, okay? But what I wanted you to see was what's on the other side, and that is this part, because this is what we're talking about when we say if we have a really strong stimulus, we can get another action potential. So as you can see looking at this, it takes a much higher than threshold in order to start the action potential again. And if you had, for example, a severe pain, okay, if you were burned, if you were stabbed, if you had something that was repeatedly going to create a stimulus in your sensory nerves and send that information to your brain, you would have huge action potentials. And they'd be going as fast as they possibly could to your brain, okay? But if there's just a slight stimulus, you may be able to push through 1 or 2 action potentials, but you're not going to have a train, okay? So this is what it means. You have to have extra stimulus in order to keep shooting off the action potentials, and they will get as fast together as they can physically get in terms of the channels opening and closing, okay? Okay. So one of the things we haven't talked about yet is how the action potential moves. We saw the picture of the axon, and it's really long, and like I said, it could go all the way from your spinal cord down to your foot, and so it has to be able to move. And so basically what's going to happen is that the part that is depolarized, where the action potential starts, it's going to spread out that positive charge so that the next section becomes more positive and reaches threshold, okay? So each section will spread out, and it will make it more positive right next door on both sides, actually, and it will be able to move, okay? So there it shows you how the spread of depolarization will make it move. Now the thing is, if you're talking about a neuron and you're talking about it starting at the beginning of the axon, it's only got one direction to go, okay? It's not going to actually go in 2 directions like it's showing here, okay? But if you're in a round cell, or if you are at the terminus with a muscle, it's going to spread out in all directions, okay? Okay, so what really happens in an axon, this is inside of your brain, is the stimulus is coming in up here. These are the dendrites. They're all touching other axons from other neurons, and they are going to get the stimulus. And the stimulus is going to collect, and then it's going to either reach threshold or not. If it reaches threshold, sorry about that. If it reaches threshold, then right here at the axon hillock, there's a decision made inside whether or not there's enough stimulus. If there is, that's where the action potential is going to start. Okay? So then the action potential is going to travel all the way down till it gets to the end of the axon, which is probably hooking up to either another axon or to a membrane of a muscle. Okay? So that's how it's going to travel. Now, since it's starting on one side, it's going to travel in one direction. And the reason it's not going to travel back is because of the absolute refractory period. It can't go backwards because those channels have just been open and they don't want to open again. Now, experimentally, we can do this. We can definitely make it go backwards, okay? But in your body, generally speaking, it's only going to go one direction because it can't go backwards because of the absolute refractory period, okay? So it's going to move itself from one end down to the other end, okay? Okay. So this is just another picture of what we're talking about when we're talking about an action potential, and the part we've talked about is called stimulus. Okay? When you saw that dendrite, you saw it had all those possible places that it could get information from the other neurons, and those are called local responses, sub-threshold local responses. Okay? So it's going to have information come in. There's going to be neurotransmitters. There's going to be ligands. They may or may not have enough information for it to get passed to the next axon. Okay? If they don't, then that is called a local response, a sub-threshold local response. And that means that it's a ligand and or a stimulus channel that's not voltage gated. Okay? Okay. When you're doing your review, you can read through all this material. I only wanted to point out one thing. Remember how I said the action potential is all or nothing? This is where there's a difference. When you're talking about a local potential or you're talking about a sub-threshold potential, you are talking about a graded response. Okay? That means there can be a little bit. There might be just a little bit of stimulation. The other thing is that when you're talking about the local potential or the subthreshold potential, it can be positive or negative. Okay? You have inhibitory neurons. They're the ones that are supposed to keep your mouths quiet while I'm talking. You got it. Okay. Inhibitory neurons are going to make the next cell, the next neuron, more negative. So an inhibitory neurotransmitter is going to make it more negative. So what you really get is when you get to the axon hillock is a summation of positive and negative local responses. Okay? Positive and negative local responses. Okay? So that's one of the reasons why you always have a situation, like I talked about using the brake and the gas at the same time. You've always got the positive and negative at the same time inside your brain. Okay? Okay. Now, if I poke an electrode into your nerve, and I give it a little bit of current, which doesn't sound like a very nice thing of me to do, what you'll find out is that you get the most response right at the point, okay, right at the point that I put the current. So this one says 0 millimeters away. Okay, so right at the point that I put the electrode in you and I make a little current, that's where it's going to hurt the most, right? As you move away, it's going to be less, okay? There's going to be less current, and there's going to be less change, okay? Remember, we're talking about a local event, okay? So, if you're a dendrite on a neuron and you're way out on the end, and you get a little teeny bit of stimulus, you've got to bring it all the way into the cell body to the axon hillock in order for it to make any difference. That means that it's got to go a long way, right? So that means it'd be far away, and you're only going to get a little bit of a response, okay? So the closer you are, the more membrane change you're going to have from a stimulus, okay? Okay. So this puts us into a point where we have to talk about some electrical concepts that are the same electrical concepts you'd talk about if you were in an electrical engineering class, okay? And that's because we use that same vocabulary to describe what's going on inside the nerve. When they decided that they wanted to have transcontinental telephone calls, and they put cables under the ocean so that they could have people from Europe call people from America, call people from in China, call people in India. One of the things that they found out is that they had to have a whole set of special mathematical equations that had to do with the fact that they had very long cables. And in a sense, if you think about those axons going all the way from your spinal cord down to your toes, we also have a cable, okay? So we have some things that we've learned about this. And one of those is that we are going to lose some of the current as it goes across the membrane, okay? So we have this one called resistance membrane, RM, okay? And then we also have some current that's going to continue lengthwise inside of the cable or inside of the axon, okay? And that is going to be less, there's going to be less resistance, okay? That's the longitudinal, all right? So when you see, and this one says in, but sometimes you also see it listed other ways, okay? So there's less resistance to going along the axon than there is to going across the membrane, okay? Now, the reason this is important is because we also found out that how big that cable is also important. So if you have a really big cable or a really big axon, then that means that there's low resistance inside to carry your message. If there's low resistance, that means the electricity is going to keep moving. Your telephone call is going to make it all the way across the ocean, okay? And if you have a very small cable or a very small axon, then you're going to have very high resistance because it's going to keep bumping into the walls, okay? Remember, those walls are made out of fat, phospholipids. That's a fat, and that's a resistor, okay? So you're not going to get very far. So what we have is called the length constant. This is one you don't have to do any calculations for. And the length constant says that in a bigger sized axon, you are going to have a bigger area and less resistance, and it's going to go faster, okay? It's going to go faster. So when I say to you something about length constant, all you really need to remember is that a bigger axon has a bigger length constant, and it means that you're going to have a better message because it's not going to get lost in the membrane, okay? You got that? Okay. So, as we know, human beings have got myelinated axons. And that means, I'm going to show you in just a minute, that we've got bigger axons because of the fact that they have a lot of coating on the outside of them. We're going to talk about that in just a sec. And up here you see a cat, and down here you see the squid, okay? And what you see is this one is pretty limited as to how fast. This is conduction velocity. How fast does your message move? How fast does the electricity move, okay? And you've got this unmyelinated axon in the squid, and it can't move very fast, whereas we have this really fast axon, okay, that's in a cat, and that means the message is going to be able to move faster, okay? So we also have myelinated axons. Let's see, what's the next? Okay, so this is what it's going to show on the outside of our neuron, on the outside of our axon, is a special cell. They actually have a couple of different names depending on whether it's inside the brain or outside the brain. But basically what that cell is going to do is it's going to wrap itself around the axon. And it's going to wrap itself around and squeeze all of the fluid that's inside its cell out. Okay? So think of it like the toothpaste tube. And it's almost empty, and you're going to start at the bottom, and you're going to roll it up and squeeze what little pieces of toothpaste out you can before you have to go buy a new tube, okay? This is called a Schwann cell, and it's wrapped itself around the axon. All that's really left is a little piece of nucleus, okay? It doesn't have to be very active. It doesn't have to have a lot of mitochondria. It's just got to do its job as like a giant insulator inside, okay? So what you end up with is this giant insulator, okay? So if you have this on the outside of your axon, then the next question becomes, what about those sodium channels and those potassium channels? Because if we just put saran wrap or cellophane around the outside of your arm, right, we just cut off the flow of information in and out, okay? So what happens is that we end up with these little spots called nodes where there isn't any wrapping. And that's where the action potential actually takes place. So, in a myelinated fiber, we have what we call saltatory conduction. I always think of it just kind of like a rabbit hopping, because all you're going to do is you're going to go from one node to the next, create the action potential, then it's going to travel inside of the nerve all by itself, and then it's going to get to the next node, and it's going to make another action potential, okay? So it doesn't have to go it can go big jumps, okay? It can go big jumps, and when it does that, it goes much faster. That's why the myelinated axon has faster conduction, okay? Oops. So that's what our nerves look like, and that's how they bounce along, having the action potentials occur at the nodes. We call these the nodes of Rands, which is what the name is up there. But you can kind of see how it's going to be first a bigger axon, and there's going to be lots of resistance in the membrane, so that means it's going to be easier for the flow to go lengthwise along the axon, and we're going to speed up the conduction. All right. So I think we have another little short video here. What happened? I lost my spot. Okay.
Hello and welcome to another episode of Interactive Biology TV, where we're making biology fun. My name is Leslie Samuel, and inside this episode, episode 24, I'm going to be talking about how myelin sheaths increase the speed of the action potential. And this is actually in response to a question that was asked by NicoDoob23 on YouTube. I'm not sure if I'm saying your name right, but if I'm not, please forgive me. This video is in answer to the question that you left. And his question was placed on episode 15 on YouTube, where I spoke about saltatory conduction. And this is what he says. He says, but why would the steps be bigger in myelinated versus unmyelinated axons? That's the real question. What is the conceptual explanation for insulation increasing speed of conduction? That is an excellent question, such a good question that I felt the need to make this video to answer the question. So this is what he's referring to. Here we have a neuron, and the axon has these myelin sheaths. So I'm going to write here, myelin sheath. And those are made by the Schwann cells. This is a Schwann cell that's actually surrounding the axon and forming that myelin sheaths. And with saltatory conduction, I spoke about how the action potential jumps from one node of Rands to the next node, to the next node, to the next node. I called that saltatory conduction. And I said that is responsible for speeding up the signal. Since you're taking bigger steps, it's going to travel faster. So what I want to do is explain how that happens. When a stimulus comes along and causes the membrane potential to reach threshold, I said that voltage-gated sodium channels open. So I'm going to say this is a sodium channel. we know that we have a bunch of sodium ions on the outside, and when those channels open, sodium is going to rush in. When sodium rushes in, it doesn't just stay here. Sodium has a positive charge, and that's going to cause the positive charges that are close to it to be repelled, and sodium is actually also going to rush down the axon. Now, this process of the charges moving along the axon, this is called electrotonic conduction. So what you have is a positive charge moving in, repelling all of the other positive charges, and the positive charges are just traveling along the axon. One of the main benefits of this type of conduction is that it's extremely fast. Okay, and that's a good thing. You want it to be fast. However, we can't rely solely on electrotonic conduction. The reason for that is this also dies down. Okay, so the charge dissipates. So let's say the threshold is negative 55 millivolts. Membrane potential reaches the threshold. Sodium rushes in, causing it to become very positive. That positive, I'm going to put some pluses here. That positive is going to repel the other positives, and those charges are going to move along the axon extremely fast. So let's say it goes down here, it goes down. However, as it moves, that charge dies down. And if we were to rely only on electrotonic conduction, if we have a long axon, the signal wouldn't reach all the way to the end because it would die down until it gets beneath the threshold. That's a problem. So what we're going to have here is, right here we have more voltage gated sodium channels. We actually have them all along, but here they're covered up. So even though there's sodium ions on the outside, they can't get in because these sodium channels, the voltage gated sodium channels here, are blocked. So as the charge moves down and it dies down, before it dies down too much, we have more voltage gated sodium channels here, and those voltage gated channels are going to open, and of course sodium ions are going to rush in. They can move again, the charges can move via electrotonic conduction. Before it dies down too much, we can have more sodium ions rushing in here, and charge moving down by electrotonic conduction. Now the problem with this process is that it's much slower, and if we were to rely on the voltage gated channels opening to cause the action potential to go all the way down the axon, that would take much longer. And of course, if you put your hand on a hot stove, for example, you want that signal to travel extremely quick. The good thing here is that it helps to increase the membrane potential. So I'm going to put an arrow going up, and E sub M stands for membrane potential. That causes a boost in the signal so that this process can continue. So we have an exchange of this fast process with this slow process. Fast process, slow process. But the way it's paired makes it so that the signal can jump quickly from one node to the next node, to the next node, to the next node. So Nicodube, to answer your question, the reason why it makes it faster is because electrotonic conduction is fast. Voltage-gated sodium channels opening is slower. So we're pairing them up so we can have a combination, the perfect combination of a fast-moving charge and a boost to the membrane potential so that fast-moving charge can continue, another boost to that membrane potential, fast-moving charge can continue until we reach all the way down the axon. I hope that makes sense to Nicodube and anybody else who has questions about saltatory conduction and how the myelin sheets increase the speed of conduction. That's it for this video, and I'll see you in the next one.
Okay. So that helped explain something that you might have been a little confused about when I was talking, because I didn't really make a distinction between them. And that is, when I talk about a length constant and how it dies out after it goes a certain amount, and it goes farther if it's in a large axon, we're talking about electrotonic. Okay, we're talking about what's also called local potential or graded potential. We're talking about that little piece, okay, where it's spreading out from the location of the action potential. Okay, so these concepts go together. They're the part that's talking about the movement or the spreading of the positive charges. Okay, and then we have our action potential, which is the all or nothing that's going to boost the signal and keep it moving down. Okay. Okay. So there is a lot of medicine that goes with the action potential, and there's a lot of medicine that goes with the myelin sheaths on the nerves. So there are a lot of natural and man-made things that will affect the sodium channels. You probably have heard about eating the puffer fish and how it goes numb. Okay. Tetrodotoxin is the toxin that blocks the sodium channels, which is why you feel numb or why you get paralysis in a larger component, okay, if you have a larger amount of it, okay. There are other things that also make that same kind of a toxin. If there's a red tide, or if you eat a lot of shellfish that were in a red tide, then they will have a lot of this sodium blocking channels and the poison, okay? If you go to the dentist and they have to give you fill a cavity and give you a drill in your teeth, then we're going to hope that they're actually going to numb your mouth up first. Some people are very brave. They don't let them numb their mouth up first. But if you get a local anesthesia delivered by a dentist through a needle, what they are doing is, again, they are blocking the sodium channels. And it's in a very limited area. But what's going to happen is, if there is no action potential, if there's no sodium channel, there's no action potential. If there's no action potential, there's no message to your brain. So you can't feel the pain, okay? That's how it works. No sodium channel to open, no action potential. So you will not feel the pain. There's going to be no message sent to your brain. All you're going to feel is very numb, because you're going to realize that, the messages are not getting through, okay? Now, there's also some problems that happen when people have diseases that cause the myelin to go. Okay, so think about this. If you have a disease that causes the myelin to go off of the axon, what is going to happen to the speed of conduction? It's going to be much slower. Okay? It's going to be much slower. Now, if that happens to the axon that goes to your toe, then what's going to happen is that the message to move your leg is going to be much slower. Okay? So it's going to affect your muscles. Okay? Your ability to walk is going to be much slower. Okay? Because you'll have to really wait for the message to go all the way to the bottom of the foot and move the foot forward before you can go on, okay? It's got to go 3 feet without having any myelin, okay? So there's a number of diseases that actually affect the myelin. Some of it are in the actually in the brain, and some of it are in the periphery, okay? So if multiple sclerosis actually means scar, and it actually causes scars or plaques. And those scars or plaques are in the myelin, okay, inside the brain. So if you took a picture of the person's brain, like an MRI, you'd be able to see it on the inside. Multiple sclerosis is a progressive disorder, which means that as time goes on, they're going to get more and more plaques. So it may be in areas that are affecting their muscles, or it may be in areas that are affecting other brain functions, but it's primarily in the brain itself. So if it's the motor cortex, it's going to affect the brain. It's going to affect their muscles because of the fact that the brain's been affected. Okay? There's some other disorders that affect the periphery. Diabetic neuropathy is one of the side effects from somebody having diabetes for a long time, especially if the diabetes has not been well controlled. And they are going to start to lose feeling. But in this case, they're losing feeling because of the fact that the blood vessels are going to die off, and that means they're not going to have good blood flow to the nerve. And because there's not good blood flow to the nerve, then the myelon's going to die. Okay? So this is more about starting with the blood vessels themselves. And unfortunately, one of the things that happen is that people can't feel their feet. And so then if they get injured or they stub their toe, they don't feel it. And then when they don't feel it, they get a big, sore. And they don't feel the sore. And then the sore gets bigger. And then the next thing you know, they have to have their foot amputated, right? Fortunately, it doesn't happen very often anymore, not anywhere near as much as it did maybe 30 or 40 years ago. But that's kind of the process. If you don't have feeling, then you cannot know that you've been injured, okay? You don't know you've got a blister on the bottom of your foot if you don't have any feeling in your foot to transmit that information. There is also a genetic disorder. I hope you're all talking because this is so interesting, right? Yes. There's also a genetic disorder that goes by the name of CMT. CMT actually stands for the three people who found this: Charcot-Marie and Tooth. That's three people's last names, okay? Charcot-Marie Tooth syndrome. It has a modern name, which is called pressure palsy. Now, if you think about what I just said, pressure palsy, then that tells you what happens. When there's pressure, it causes paralysis, okay? So what actually happens is that if this person has pressure on their hand, oops, so sorry. If they have pressure on their hand, or if they have pressure on their leg, or if they have pressure on their back, they are going to lose the myelin, okay? So, it's a dominant disorder, which means you only have to have one parent that has it, and it's going to cause a change in the myelin protein, and when it changes the myelin protein, it makes it very weak, okay? So that is what happens, is it makes the myelin protein very weak. So I'll give you some examples of what happens. Anybody ever gone to the grocery store? I'm assuming you all helped your mothers go to the grocery store, right? And now you have to do it for yourself. So you're carrying everything home, and you end up buying more than you thought you were going to buy. Maybe you've got milk, and it's really heavy, and you're carrying those plastic sacks, and you have all those plastic sacks cutting across your hand in the same place because you're carrying them like this, right? Okay. So when somebody has this disorder, by the time they get home, they're going to put down those plastic sacks, and they are going to have lost the myelin in their hand below the point of pressure. Okay? So they're not going to have very good feeling or conduction in their fingers. Okay? And it will take a couple weeks before it comes back. Okay? So if you did that or I did that, probably our hand might hurt, and we might even feel a little numb, but it's going to be back in, 5-10 minutes. We're going to feel fine, right? But they're going to lose the myelin, and it's going to take several weeks to come back. Now, another example of what can happen is, say somebody hurts their back and they have a bulging disc. A bulging disc means that there's a piece in your back that's swollen, and it pushes against the nerve. So The pressure from the pushing against the nerve is actually going to be the pressure that causes the myelin to go away. So what if that happens in your lower back and you lose the myelin all the way down your leg? It can take up to 2 years for it to come back. Okay? So for 2 years, you're probably going to wear a brace on your leg so that you can keep the stability in the leg as you walk slowly. Okay? So that's what CMT does. And you can see from these little pictures here, it also causes problems because people so frequently lose the myelin and the nerves in their toes that it starts to cause the hammer toes and the claw feet because the muscles will all pull up when there's no information coming from the nerves. Okay. So this is one of the most densely packed lectures that we have for the whole semester.